Welcome back to the lecture series on GPU architectures and programming. So, in the previous lecture we have been discussing about convolutional neural networks, and we are due to start with how to define parameters and of the neural network. So, essentially in a convolution layer we have a 3D weight matrix or an array of 2D weight filters, and they represent the learnable parameters like what should be the suitable values of these masks, right. And also the dimension of the output is dictated by these 4 hyperparameters, which is what is the number of filters and the filter dimension, stride and zero padding, right. So, essentially the architecture of the CNN. So, again we will just remember what do we mean. So, essentially we are talking about how many filters to consider, that is like how many weight matrices to consider, what will be the dimension of those filters or the weight matrices, and then when we are performing the convolution also has an important parameter, which is the stride of the convolution, and the other thing is the amount of zero padding that we will want to do, right, because we will soon see that how that affects the convolution operation. Now, why are these the hyperparameters? Because essentially your neural network architecture, how it really functions, it depends on this initial unknown quantity, right, because it defines the architecture of the neural network, that I mean how many filters to take, what are the structures of the filters, and finally once you decide the hyperparameter set, then you are trying to discover what will be the value of arguments inside those filters, and that is the weight matrices, so that you get the loss function minimized. So, coming to the convolution layer. So, formally speaking, the layer takes as input a 3D image volume, and the dimension is the number of channel cross height cross width, and the hyperparameters are, let M represent the number of masks or filters, F represent the size of the filter, right, I mean it is an F cross F matrix like that, S is the stride, and P represents the amount of zero padding. We will soon see what that means. Now, what is this layer going to produce? Is going to produce a 3D volume of dimension C prime cross H prime cross W prime. So, as you can see that there is a, I mean in terms of dimension, I have the channels from the input, they are now changing to C prime. Why? Because the input image gets multiple different filters applied, right. For example, if you see here, I have a 3D image, I applied a 3D mask, I got one output, because I essentially they are summing up to one mask, right. So, the number of outputs that I really get, that depends on the number of masks I apply. For example, here if I apply 3 masks, each of them operating on the 3D image, the 3D masks, each of them are going to give me 1 2 cross 2 output. So, for using the 3 masks, essentially I get a 3D output like this, right. So, essentially C prime is M, that is the number of filters, but what is H prime? H prime is essentially the height, the modified the height of the output, and W prime is the height of the width of the output. Now, how to determine that? So, let us consider some examples to determine that. And also there is some important parameter, that is the zero padding, that how much of extra zeros should I surround the image with, so that I get to decide how many, what should be the output image dimension. We will see what that means. So, consider P equal to 1, that is the padding is 1, that means we have this as the original image. So, this is my image, right. So, if I just write down for this image, height is equal to 1 2 3 4 5, width is 5. So, these are all 5, right, and then I decide to put one layer of zeros, right. So, the padding P is 1, right, like we already have here. So, that increases it, right, the area on which the mask can float around. Once I put padding of one layer, then I am essentially saying that, well, the mask need not start overlaying the image from this point, but rather it can start from this point and it can come up to this point and go up to this point, right. So, that increases the number of shifts that the mass can make, right. Why is that important? Because that decides the output images height and width, right. So, as you can see, if I consider p equal to 0, then this mask of size 3 cross 3 can make how many strides? It can make, I mean can make how many movements on the x axis? It can have one location, then the next location, then the third location, right. So, that makes it that makes the output images width to be 3, but now with the 0 padding, what are the maximum number of locations on which the mask can traverse in the x direction. So, as you can see, I can really start here, then I can move the mask here and then here like that, right. So, 1, 2, 3, 4 and 5, because once the mask comes here, I am done, right. So, 5 possibilities, that makes w prime equal to 5, and since h is also equal to w. So, the mask can also take how many locations in this direction? 1, 2, 3, 4, 5, right. This is the last possibility, right. So, h prime equal to w prime equal to 5. Now, let us now go and work back on the formula. So, this is our formula, right, 1 plus h minus f plus twice of p divided by s. So, let us see how it comes. Plus twice of p divided by s. Now, in this case, since I am moving the mask by one position at a time, so the stride s is equal to 1, right. So, if you just check it out, so effectively I have s as 1, the height is 5. Now, of course, the mask has a width f which is equal to 3. That means, after this point it really cannot move. So, the entire height minus 3 plus you get 2 extra positions to move because of the padding, right. Since padding is 1 position this way, 1 position this way. So, 2 into 1, right, and it should work out to 5 minus 3 plus 2. So, that is 5 minus 1 by 1. So, that is 4 plus 1, that is 5, right, it is coming out properly. And similarly, the calculation can be done for w prime. So, for w prime I will really have 1 plus w minus f plus 2 p by s, right. But what about modifying the s? If you modify the s and make it 2, then naturally the strides get bigger. So, you get one mask position here, then the next mask position will be here, right, because this is then s equal to 2, right, and then the last mask position is here, because again you make another stride, right. So, 3 positions, right. So, I expect if I put s equal to 2, it should really give me the result as 3, and that is going to happen if you put s equal to 2. So, this is instead of 1, you have 1 plus 4 by 2, that is 2. So, you get a 3 here, right. So, that is how it works. So, with p equal to 1, this is how you make progress and compute the convolved output. You are moving in strides of 1 and you get all the values computed. If we just show a small simulation of s equal to 2, just like we discussed, you will move in hops of 2, and similarly like just like we discussed, the output will be 3 cross 3, right. So, just to relate what is the difference now, instead of doing the matrix multiplication, you are now doing convolution, and the operation essentially performs dot products between the filter weights and the patches of the input image on which it is working locally, right. By patch I mean the region of the input image on which you are overlaying the mask and doing the operation. Now, a common approach, like if you want to do the convolution operation of the CNN efficiently, is to leverage this fact and formulate the operation of the convolution layer as a matrix multiplication. So, let us try and understand what is the I mean advantage. So, just like we discussed, convolution is just individual dot products, right, of the filter weights and the input image. We already have efficient routines for performing matrix multiplication and different optimizations. So, if we can just adjust the masks weight values and the images pixel values in such a way that the operation reduces to the matrix multiplication operation, that can really help us to get the job done using available or optimized matrix multiplication routines, right. So, that is the trick we are going to play for implementing convolution efficiently. So, let us see how it works. So, this is the very simple and nice example. So, consider on the left hand side you have these masks, right, you have 3D masks, and what you really want to do is you have mask M1, mask M2, and you have mask M3 at some region of the computation. What you really want to do is you have this 3D image and you want to transform this 3D image and get the transformed outputs for all these masks M1, M2 and M3. And so, it is just like you have the input image and you want these transformed outputs to flow to the next layer, and they can really be done in parallel, right, because they are quite independent operations. So, as an optimization, what we can do is we can arrange the masks and the image data values in such a way that finally the operation of computing the transformed outputs will boil down to the matrix multiplication operation. Because as we have seen that individually the mask weights will be component wise multiplied, will get component wise multiplied with the image pixel values, right. So, what do we really do? Is very simple. Let us take mask 1. For mask 1, you arrange all the values in a single row for the first layer, and then again for the next layer, then again for the next layer, right. This is all for M1. Do the same thing for M2, do the same thing for M3, like that, and prepare one large matrix. What will be the size? Of course, the number of masks times the size of each row. The size of each row is of course f square, right. So, this is f square, f is equal to 3 here, right, f cross f. I mean I am speaking of capital F, which is the width or height of the filters, right. So, f square times the number of channels, 3 channels. So, f square cross 3, that is the row size multiplied by the number of masks. So, that is one large matrix that you are preparing by using all these masks. Why you do this? Well, that becomes clear when you look at what transformation we make for the image. So, this is the image on the right hand side, 3 channels. For each channel, and sorry, here we are talking about different masks, right. Each of them are 3D masks, and each mask finally gets to one row, right, and each of them, and the second row is for mask 2, third row is for mask 3, like that. Here I have the image, and for the image I have 3 channels. For each channel I have a 5 cross 5 matrix, right. Now, if you think what is really going to happen when you do a normal computation, let us say I am trying to convolve the image with mask M1, what am I really supposed to do? So, I will take the first layer, let us say this brown layer, and then I am supposed to overlay it with this image, right, at this position, then the next position assuming a stride of 1 and so on and so forth, right. So, that gives me how much for the first position, for this position I am going to do a transformation, for the next position again I am going to do another transformation, right, and for each of the computations I am going to calculate and store the value, right. So, how do I do it in this in the case that where I have modified these masks into the matrix that I have shown here? How do I really do it? Because it is expecting the input data now in a different format, right. So, what I am really going to do is I am going to duplicate this data into multiple positions. What I do is, let us say this initial position of the mask, the initial position would have been here, and I am supposed to do f 1 multiplied by I 1, f 2 multiplied by I 2, f 3 multiplied by I 3, f 4 multiplied by I 6, f 5 multiplied by I 7, like that, right. Since I have I 1 f 1 to f 9 in a row, I just put this position of the data which is here in the first overlay position of the mask. I just arrange it in the form of a column. So, now the column contains I 1, I 2, I 3, I 6, I 7, I 8, I 11, I 12, I 13, right. As you can see, if I multiply this row segment, let us say, if I just multiply this row segment with this column up to this, I get the value I was looking for, which I am supposed to put in an output. So, if I just write what I am supposed to do after all this, right. So, for M 1 I am going to do these multiplications and I am supposed to get 3 cross 3 matrix, right, 3 cross 3 and a stack of them considering the other components, this, right, they are going to give me a stack of this kind of 3 cross 3 matrices, right. So, now what I am doing is I am supposed to compute each of these locations and they come out when I multiply this with this row segment gets multiplied with this column segment to give me this value, right. Again this row segment when it gets multiplied with the next column segment is going to give me the next value, right. So, what is this column segment? Now, I am going to shift the mask here, right. So, now I am going to take values I 2, I 3, I 4, I 7, I 8, I 9. So, I 2 up to I 14, right. So, essentially this much, as you can see from I 2 to I 14, and at the last I am expecting I 3 to I 15. So, I 3 to I 15, right. At the last I am that last means this location. So, in this location I am expecting these values, right. So, that is I 3 to I 25, as you can see I 3 to I 25, right. So, all I am saying is I want these individual values to be computed, right, but what I do is I arrange them like these columns, I arrange the input mask like this row segment and I multiply this row segment with all these columns to get the first layer of the 2D output done, right. Now, you can understand the same thing is going to work for the next set of channels, right, because now if I just continue with the operation, then whatever mask values are there in the next layer of M 1, they get multiplied with similar things here, right. And how does that help? Because I am not only going to compute this layer wise weighted values, weighted sums, but the next thing is I am supposed to add them across layers. Since I am supposed to add them across layers, here in this case it is getting reduced to an entire matrices row multiplied by column computation, right, because I have already computed M 1 up to this position. Then you compute all the locations from F 1 to F 9 for the intermediate layer in the mask, and you are already having the data for this second layer arranged right here, right. So, all you get is you are, while you are computing these locations, you are also simultaneously computing the backward location for the same mask. That means, you are computing this as well as this value, but these are not the individual values that you are finally interested in. What you are finally interested in? You are essentially interested in this entire column, entire row, pairwise multiplications, and then the final addition. That is going to give you the final 2D output matrix considering one mask M1, right. I hope this is clear. So, once you do this, you get for M1, what is going to be the value here, the next value, and so on and so forth, right. So, for M1 I am finally expecting what 9 values, right, and then they get multiplied here, and finally, what do I really have essentially, and when you add them up, you are going to have one value here, the next value like that, so on and so forth. But overall, you have successfully computed the entire thing for the 2D image, right. And then what are the total number of positions that you have covered? If you look at it minutely, it is exactly same as the size of the output, right, considering one mask. But finally, you are going to have so many of them, right. So, the same thing will now repeat for mask 2, because you now have the entire mask 2 captured in a single row. So, you just keep on applying this mask 2 on all the columns individually, right. So, in that way you will have all the values that you are going to compute for mask 2 available for these columns, get them working with the rows, and you get the final results for mask 2 computed in the next row. First row is computing all the values that you would have required for mask 1, right. So, this is essentially mask 1 transformation with image I. Next row is mask 2 transformation with image I. Next row is mask 3 transformation with image I, so on and so forth. I hope this is clear. Now, how are the entries holding up here? For mask 1, how many entries are going to be there? Well, it is really basic the number of overlay positions I can have for mask 1, which is essentially 3 cross 3. So, I will essentially get 9 entries, and that is what is going to happen, because I have actually got all the 9 possibilities for mask already captured here, right, in terms of each of the columns. So, I am really having 9 columns here. So, here in one row with 9 entries, I am going to get the entire final output for mask 1, then for mask 2 in the next row, then for mask 3 in the next row, and that is how it continues, right. So, as you can see, the whole point of doing this transformation and the multiplication is I am successfully able to convert this convolution of many weight matrices into a matrix multiplication problem, where all these convolutions outputs are computed in parallel, right. What is the overhead? Of course, you have some data overhead, because essentially you are creating a data layout where entries are getting duplicated. Why is that happening? Well, here you do not have any duplication, you are just considering each of the masks and taking all of that together into a large matrix, where you have arranged it in a smart way, so that the number of rows is same as the number of masks, the number of columns is same as mask size times the number of layers, which is obvious here, right. But so, there is no duplication. The duplication is the way that you are arranging the image, right, because here you are for each, let us say this is the one layer of the image. For that, you have got 25 possible values, and you are duplicating them because you are trying to keep each of the possible overlay instances of the mask separate. Since you are going to have 3 cross 3 overlay instances, 9 overlay instances. So, you are having I2 here, I2 here, you are having I3 here, I3 will also be here. So, there will be many duplications like this, right. But as we are considering a parallel programming language, so essentially I will have multiple threads who will be creating this data structure in parallel and then engaging into the matrix multiplication task. So, the creation of this image to column, that is what it is popularly called image to column operation, is available in most of these free softwares that deep learning libraries like Caffe, and this is one of those examples which you have just given. I mean, you can have a look at it with the slides that we provide. I think it is not required that we keep on talking about what is happening here in each of the lines. So, just to repeat, all we are doing is we are launching sufficient number of threads, so that each thread is responsible for copying one possible overlay of the image, right. I mean the mask positions. So, for this I will have one thread will do the copy here, another thread will do the copy here, another thread will do the copy here, another thread for this, so on and so forth, right. So, in that way the threads will be doing and doing the copy operations in parallel, and then well, will there be some coalescing happening here? I believe so, because if you see, let us say one thread is doing copy of all this data, the next thread is doing copy of these data points. So, naturally, I mean when this guy is copying this one, the next one is going to copy this, the next thread may be copying this. So, you have scope of memory coalescing and successful use of shared memory and all that, which you can really explore using the optimizations we have discussed earlier, right. But if you just look at a vanilla code that we have provided in the next slide, we are not really making use of shared memory or other things, but we are engaging multiple threads to do the copies parallelly from the global memory, and you can check as a task how much is the scope for memory optimization here, how much is the coalescing here and all that, right. So, that is kind of a disadvantage we can say, that when I am doing the image to column approach, I require extra memory, since some of the values are replicated multiple times in the columns. But the good thing, as we have discussed, is that there are really many efficient implementations of the matrix multiplication, or the way people popularly call it is general matrix multiplication or GEM, and people can take advantage of the GEM operations once this image to column transformation is really done. For example, there is this very popular CU-BLAS library which contains efficient implementations of GEM. Some of those GEM optimizations are also things that we will be discussing later on. Well, that would be all about our convolution layer. The next thing that comes into space is the pooling layer, because if you remember our convolution architecture, so pardon us, we will just go back once. So, here we talked about these multiple layers. So, input layer is there, then convolution, then pooling, and then the ReLU layers, right. So, essentially the pooling is nothing, but you are doing a downsampling of the image. So, to summarize, is typically a spatial downsampling transformation. The inputs of and outputs both will be 3D image volumes, right, and but there are not really any learnable parameters unlike the CNNs and the convolution layers, but what you do is you are trying to reduce the input image size. Why are you interested in the pooling? Because remember that while in the front the input layer you may have these heavy images with multiple channels and all that, but at the end if you are doing a classification kind of problem, you are only interested in this class scores, right. So, you want a linear array with different scores filled it up, right. So, there has to be intermediate layers interspersing the convolution layers, where you will try to reduce the output image sizes, right. Now, there are several possible pooling operations. Typically, one is a max pooling and another is the average pooling. So, what does that really mean? So, here by let us say this is a bigger dimension image and I am trying to reduce it to a smaller dimension. So, I can do a max pooling, that means I choose a mask of this size, and for all these values I just put the maximum here. I then I just move it over a stride of the same size, and again I put the maximum value here. So, this is just a transformation which is kind of downsampling it, because I am moving from a more information representation to a smaller information and compact representation. I am losing information here. So, that is the downsampling, right. So, I could have done max operation, or I could have also done a average operation. So, both are possible in pooling layers, right. So, just to formalize, I am considering 3D images here for pooling, number of channels times height comma width, and then the hyperparameters of the layer are, well, again I have to decide that what is the filter size that I am going to talk about. For example, in this picture this is a 3x3 filter and it is moving in strides of 3. If I increase the stride size, I am going to have more amount of downsampling, as we can see, right. So, once I choose a filter size and a stride size, what the pooling, out of the pooling I get a modified transformed output of dimension C prime, H prime, W prime, where naturally the C prime remains same because nothing changes here, the number of channels is same, but of course, the height and the width values get modified, following similar formulas like we have elaborated earlier. So, it is simply 1 plus h minus the filter size and you divide by the stride. So, that gives you a smaller and simpler image, a transformed image to work with, right. You can just do a simple implementation of pooling kernel. So, this is also taken from available repositories. Again, we are not really getting into discussing this operation, it is quite simple, and the idea is that by doing the pooling, you are conveniently decreasing the transformed image sizes, so that at the end of the pipeline you really get the class scores. So, the other layer that you have is the activation layer, which is very similar to the ones that we have been talking about earlier, and for the activation function in CNN, the standard one that we use is the rectified linear unit, which we have discussed earlier during our discussion on Valena neural networks, right. So, if I look at the structure of an end-to-end CNN, you have a image here, and then you will have convolution layers followed by pooling layers, again convolution layers followed by pooling layers, like that. And of course, after every convolution you are also you are going to have the ReLU layers also, right. So, again if I just go back into that slide where we define the CNNs, so that is what you have: input, then convolution, pooling, and then the ReLU, right. And this will this will repeat many times. You have convolution, again the pooling based downsampling, and then ReLU and all that. And so, the ReLU is like we have discussed earlier, it is giving you the required nonlinearity, and so in that way you keep on transforming the image and also downsampling its size, and at the end you have a fully connected layer, just like our normal neural network architecture, and the fully connected layer will be reducing this the transformed image to the final class scores for the output layer, where you have the different number of nodes as the number of classes that we are talking about, right. So, that is how the CNN pipelines are arranged. The next thing that we will be looking into is how the data really flows across this pipeline, how the back propagation and of course, the feed forward propagation works specific to CNN pipelines, what are the computations involved and how are they carried out. Okay. So, with this we will end the current lecture. Thank you for your attention.